So it's not enough that you can calculate the volume of a solid revolution by the disk and washer method. We're going to work on the shell method. Now the shell method starts by doing something a lot different than what we did with the disk and washer method. And that is, instead of taking a slice parallel to the axis of or perpendicular to the axis of rotation, we're going to take a slice parallel. So for us, if we're rotating around this axis, is a parallel slice going to be a dx slice or a dy slice? Yeah, parallel. So let's see. That would be parallel. What's the width of that slice? Is that dx or dy? It's a dx slice. Good. So that's the big difference. And when I grade your exams, on these types of problems, there's a lot that goes into them. And one of the first things I look at, relative to your method and how you do things is, what kind of a slice do you take, dx or dy? Now, if you rotate that around the y-axis, what you're really going to get is kind of like a small cylinder. And you can kind of see that here with respect to this cylinder. And what we want to do is we want to calculate the volume of that one cylinder. And then we're going to add up the volume of all such possible cylinders through integration. So here's our little trick. Here's our one little cylinder. We want to calculate its volume. I'm going to cut that little cylinder down a seam, and when I unfurl it, I got something like this. Now essentially that's a really thin rectangular solid. So let's figure out how to calculate the volume of a rectangular solid. Well, there's going to be a few dimensions. One of the dimensions is going to be the height. Another dimension is going to be the width here. But that width really comes from a circumference, right? What you're doing is you're unfurling this, so that circumference is your width. So the width is going to equal 2 pi r. And there's one last little dimension that we need to account for, and I can't really write it there because I can't write in such a small font, but that's going to be the thickness, or the other dimension, length, width, and height, whatever you want to call it. It's going to be this dimension. So we want to find the volume of one shell. Volume of one shell. So let's see what we can do about that. So the volume is going to be equal to the width times the height times dx. Now that dx term is important. I remember harassing you about it in Calc 1. It's going to continue here in Calc 2. The fact that we've got a dx term here tells us that we want these other terms as functions of x, that variable. So, okay. Let's see if we can't get a few of these dimensions. Now, one of them was the height. The height is going to be our top minus bottom. So I'll do these one at a time. Our height, which is our top minus bottom. And I'm only doing this top minus bottom stuff for future problems where you might not have a bottom that's the x or y axis. The top minus bottom is really going to be x, y. Is going to be y minus 0. But because we have to write this in terms of x, we should really write it in terms of, let's see, a is 6 and b is 2. So it really should be 6 times the sine of bx squared, or 2x squared, minus 0, or just 6 sine of 2x squared. So that's our height. Now the width is going to be a little bit more work, so let's work on the width over here. The width is really going to be 2 pi r. That's just the circumference of a circle. But what's the radius going to be? Well, the radius is going to be this distance. Now I put general coordinates up here. Can anyone tell me what that distance is going to be from here to here? What's that radius going to be in terms of our variable? It's nice that you're solving for it, but you're actually working a little harder than you need to. That distance for this general slice is just going to be x, or x minus 0, or just x. So the radius is just x, or overall our width is 2 pi times x. Okay, I think that pretty much does it. The only other thing we need to fill in is our dx, but we already got that there. So the volume of one shell, let's kind of get to the final formula for this. That volume is going to be 2 pi times x times sine of 2x squared, like that. So your width times your height times your dx. Nice. So that's the volume formula for one shell. Now we need to add that up for all such possible shells. So that process, really starts with a Riemann sum, and then the values of delta x get really, really small. You take a limit, etc. We're going to bypass all that, and I'm going to take the 2 pi out in front. 2 pi times the integral of 6 times x times sine of 2x squared dx. There's one thing missing, though. What's that one thing missing? Yeah, limits. Limits. So the bottom one's going to be 0. The top one, they kind of give you a hint there. It's a square root of pi over b. So in our case, b is 2. So let's just use that right there. And let me put a little guide or direction if you're looking at these notes later. This value here comes here. So square root of pi over 2. Looking good on that. All right, that's the setup. That's the big part of this. You're probably looking at 6 points out of 10 so far if you're setting this up for me on an exam. The rest, of course, would be to finish this up and get it right. So there's some other points involved, but getting the setup is a big thing. All right, there's a lot of programs out there, Wolfram Alpha, Photomath, ChatGPT, that can finish solving this, but they're not necessarily always going to know how to set this up for you. So that's where I'm going to place my emphasis, is on getting this far. Let me pause for a second. Are you okay with how we got here? It's a good place to reach out. Yes?
How do you set up the integral?
How do you set up the integral?
Yeah, like how do you, what are the steps for it?
All right, so really what you're doing is, for the integral, is setting up the integral from your a to b of the volume of one shell. That's essentially what we're doing. So that volume formula really turned into the volume formula for a rectangle. It's height times width times this, your thickness of your slice, either dx or dy. Now the most important thing that I really need to emphasize is that when you're taking your slice, that you take it parallel to the axis of rotation. Sometimes on an exam, what I'll do is ask you to set up both ways, set up by shell or disk and washer, and then finish solving it one way. All right. I don't need you to solve it both ways, but I'd like you to understand both ways. And there's good reason to understand both ways that I'll talk about more as we go through. All right. Anything else? So let's take a look at example A here and see if we can't finish it up, or at least discuss how we'd finish it up. So it'd be the integral from 0 to square root of pi over 2, 6x sine of 2x squared dx. Now, if you're stuck doing this on an exam, if you actually had to do this, well, let's see. Kaiser was pretty good the other day in spotting an antiderivative. How would you find an antiderivative for this one? Tell you what, let me take the 6 out in front, make that a 12 pi, 0 to square root of pi over 2, x sine of 2x squared dx. How would you finish this one up in terms of, Clyde?
Use substitution, set u equal to x squared.
Yeah, I'd probably do the 2 in there as well, just to get rid of that. So let's let u equal 2x squared, and then we'll kind of fast forward a little bit. Du would be 4x dx, so that's differentiating with respect to u, or with respect to x, and then multiplying both sides by dx. Looking at what I've got here, I've got an x and a dx term. So for those who are new to Jeff Parent, the way I like to roll with these is I like to solve for what I have in the integral. And that is, I want an x and a dx by itself. So if I multiply both sides by 1/4, then I'll get 1/4 du equals x dx. There's one last thing I need to do before I make my substitution. What would that be? Anyone know? Kaiser?
Limits.
Yeah, need to change our limits. These limits are for x. I need new limits for u. So let's call this u of x is 2x squared. I need to find a couple things. First one would be u of 0, and the second one would be u of square root of pi over 2. U of 0 is just 0. I don't think I need to work through that with you. But, yeah, u of square root of pi over 2. All right, let's pay attention to that one for just a moment. I'm going to take and square that and then multiply by 2. What would that give me? When this squares, I'll get 2 times pi over 2, just pi. Yeah. So there's my new limits. So, wow, that's going to make things a lot more user-friendly. I'll pause here for a second. How are we doing on the limits and the u substitution in general? Doing good? Trying to remember, is it Sophia? Okay, yeah.
Are we gonna go over all the ways to find the integral, like integration by parts?
That's coming up in section 7.1.
Okay.
Yeah. So we are going to go over more techniques of finding antiderivatives. This is just the only one we have right now. All right, that's the only one I expect from you. So let's see, that's going to be 12 pi integral from 0 to 2 of, well, let's see, sine of u times 1/4 du. Now let's clean this up just for our own sake. The 1/4 comes out. That'll give us a 3 pi out in front. Integral between 0 and 2, sine of u du.
It's supposed to be 0 to pi.
0 to, oh, pi, my bad. Thank you. Thank you. Don't have my Photoshop in here. All right, so let's make that a pi. What's the antiderivative of the sine of u? Now you got to think carefully on this one. You want to find something that when you differentiate it, you get the sine function. What would that be? Yeah, negative cosine. So it's going to be 3 pi, 0 to pi of negative cosine of u. We can take the negative out in front, get negative 3 pi times this cosine of u, which is negative 3 pi times cosine of pi minus cosine of 0. Negative 3 pi times, what's a cosine of pi? Negative 1. And the cosine of 0 is 1. So basically you get negative 3 pi times negative 2, or 6 pi. Now there's something that's a little bit reassuring about this last answer. You have these negative numbers, but the negatives cancel each other out, and at the end you end up with a positive number. Your answers for these types of problems should always be positive numbers. You shouldn't get a negative number when you're trying to find the volume of something. All right, good one, good one. Anything on example A that's like troubling you a little bit? Let's try again with example B. This time I've kind of got your little wedge drawn out for you. We're going to rotate this around the y-axis. So this is our axis of rotation. If I tell you to do this one by the shell method, you have to take this kind of a slice. Why? Why do you have to take that kind of a slice? Andreas? Yeah, it's parallel to your axis of rotation. So there's no choice if you're doing this by the shell method. Now when you rotate that around, you're going to get a very thin rectangular solid. We want to find the volume of that rectangular solid. Now one thing that's going for us is the thickness. That's your dx term. But how about the height? What do you think we can put in terms of the height? What would be our height for that one? Jameson?
Isn't it 2 to the cube root of x?
Yeah, so the height is really going to be, y minus 0, and y is really just 2 cube roots of x. 2 times the cube root of x. Now it might be simpler to write it as 2 times x to the 1/3 in terms of your integration. But yeah, perfect. And last but not least, we need to know the radius. Now sometimes it's helpful to put a little point on this dy slice or dx slice, x and y. And then you can draw in whatever figures you want. So the distance between these two, here to here, that's your radius. So what's that distance? What's r? Yeah, it's just x in this case. Now if you're rotating around a line, say x equal -1, then your radius would be x minus -1 or x plus 1. So you're going to have to do that subtraction. But overall, that means this edge is going to have a distance of 2 pi times x. Let's put that together for the volume of one shell. And I'll give you a minute to try and put that together before I do it here. If you're watching this later, pause button for yourself. Try and find that volume. And then see if you can't fill in the integral for that as well. So let's just fill things in from here. Curtis, maybe you can help me out. I want this times this times this.
I did 2 pi x times 2x to 1/3 dx, and then I brought out the 2 pi.
Okay. So 4 pi, and then these can combine, right? X times x to the 1/3, that's going to be x to what power?
2/3.
4/3, there you go. Yeah. So 1 plus 1/3 would be 4/3. Great. Thank you so much. Let's think about the overall volume of this. So for the volume, we're just going to integrate this. Are we comfortable with that part? Doing good there? Lionel? Yeah? Okay. Thank you. So the volume overall is going to be given by 4 pi, which I'll take out in front. The integral from something to something of x to the 4/3 dx. Now, what are our limits going to be? To get the limits, you have to think about where this slice can be taken. Where can this yellow dx slice be and still be in the region that represents what we're rotating around the y-axis? So in our case, it starts at 0 and goes to 1. Okay. So as far as this is concerned, that's the formula for our volume. That's a lot of the work that we're going to need to do there. Gina, is there something about this that maybe I went over too fast? You okay with what we've got here?
Yeah.
Okay. All right. Good deal. As far as the antiderivative of this is concerned, you're going to add 1 to that exponent. What would I get? 7/3. So it's going to be x to the 7/3. Dividing by 7/3 is the same thing as multiplying by 3/7. So I can bring that out in front. That's going to be 12 over 7, or 12 pi over 7 times the function 0 to 1, x is 7/3. Fortunately, plugging that in is going to be pretty easy. You're just going to get, 1 minus 0 or 0. Our overall answer should be 12 pi over 7. Nice. At some point, I'm going to have you finish some of these things by numerical integration. You remember last time what I said about numerical integration? What kinds of functions am I going to say, all right, yeah, just do that one by numerical integration? Polynomials, yeah. Polynomials, I'm not really interested in making you go through all the work doing that by hand. Wonderful. Thank you. All right, let's move on to example C. This time we're going to rotate a figure around the y-axis. And I've kind of got to start it a little bit, but maybe I'm misleading you. Maybe I'm tricking you. You tell me. What does it look like we're set up to do with this picture, with this problem? If we're going to rotate around the y-axis. What's that? Yeah. So, first of all, why is this a disk? Can anyone spot that one? Why is it a disk? Yeah, this curve isn't flush with the y-axis. In order for this to be a washer method, it would have to be completely flush or smashed against the y-axis. And secondly, how come this is a disc and washer method as opposed to a shell method? What can you just look at this and say, yeah, it has to be, this method?
It's taking the wrong slice.
Perpendicular.
Yeah, this is perpendicular to your axis of rotation, not parallel to your axis of rotation. So we're just going to take just a second and set this up. I'm not going to worry about the finished part of it. But let's set this up for the disc method, or washer method. So this is going to be a washer. All right, well, for our washer, remember we're going to have the volume of one washer. So volume of one washer. And if you wanted to look back at this, you can look at the previous video in this series and do that there. But our formula for that is going to be pi times r2 squared minus r1 squared times the thickness. Now in our case, what's the thickness going to be measured in? We have a dx slice or dy slice? That's a dy slice. So dy. Now, the radial distance that we're dealing with, that's going to kind of depend on where we're at in terms of this figure. But let me put in, a couple little spots here, an x and y, and another x and y. Although these two x's are different. Sometimes I subscript them, sometimes I don't. We're rotating around this axis, so we're going to have this radius here, and another one here. Is this going to be our R1 or R2? The outer radius or the inner radius? That's going to be your inner radius, so that's going to be your R1. This is going to be your R2. That's going to be your outer radius. So one way to think of these is, all right, well, that distance is just our x, or x minus 0. But unfortunately, that's not really good enough. We need to have this in terms of y. Now, good news for us in this problem, we've got x as a function of y. So we can just write it as 4 plus y minus 6 squared. And that's your inner radius. How about the outer radius? I wrote an x. I really shouldn't have wrote an x. There's something better I can put instead of the x. Can anyone see what that would be?
20.
Yeah, it's going to be a 20. So 20 minus 0, or just 20. Nice. So, all right. That gives us our expression. Let's find the volume of one of these washers. That's going to be pi times, wow, this is going to be a big mess, 4 plus 6 minus y, or 4 plus y minus 6 squared, squared again, minus, actually that's the wrong way. I should have had the 20 squared first. My bad. Hopefully you can maybe just squeeze that in for yourself. Pi times 20 squared minus 4 plus y minus 6 squared, squared again, dy. Whew. And then you can make that 20 squared 400 if you want. Please, if you're squaring these things out, don't apply the square to just each of these terms. This is not y squared plus 36 or y squared minus 36. You got to FOIL that out, likewise here. But overall, this is a polynomial. So you could finish solving this with a polynomial. The one thing that you're going to have left to do, though, is to figure out, well, what are the heights involved here? Where do I integrate from? So if we want to find the volume overall, it's going to be pi times some integral, 400 minus 4 plus y minus 6 squared again dy. Now the top interval, where's the top going to be at? What's the top limit going to be for us? Anyone spot that one? 10. The bottom one, I'm thinking 2. Looking at the graph. If you weren't sure, how could you decide? How could you solve for that?
The point of motion is 4, and if the
Is it
top-
4? I think it's,
y equals 4.
I think this would be a 2.
I thought, sorry, y equals, never mind.
It's all right. It's all right. Yeah, so you could set these two equal to each other, this one, and solve. You'd subtract 4, take the square root, and you have y minus 6 equals plus or minus 4. And then when you solve, you'll get both of these. So, let's see. Yeah, this one looks like a 2. And that's it. This one you could finish with fn int. But take a look at this, the one below it. The question to you, and I'll pause it for a minute here, is can you do this with the washer method? Can you do this? So think about what we would need with the washer method. I'll give you a minute to think about that. Not the washer, the shell method. Yeah, let's get rid of this and put shell. My bad. Can you do that with the shell method? Now confer with your neighbors. Can you do that with the shell method?
I know what you mean. But when we started seeds, I think you said you can't do shell.
You have to get the,
In terms of you're still
multiple integrals around there. Just like change it. Solve this in terms of y. I think maybe you could, but
I think it's like,
that's my other
like here it's like flush with the axis perpendicular to axis rotation, flush here, it's flush here, and this, it's flush. Or I guess it needs to be flushed out.
Okay, so what's your verdict? Do you think we could do this with the shell method? First things first, what kind of a slice would you be taking for the shell method if you're going to do it with the shell method? Has to be parallel to the axis of rotation, which is going to be your dx slice. Now, if we take a slice that's parallel like this, can we do that? Is that going to be something we could easily do? No. Why not? Sophia, what would be difficult about this? What's the thing that jumps out about, oh, that'd be a problem? Yeah, the height is between, 2 points on the same curve. It's going to be very difficult to characterize that height if you're going from a curve to itself. So that's kind of a big red flag for you, is try not to measure a distance between a curve and itself. So yeah, at that point you say, we're going to need another method. All right? So try not to measure a distance between a curve and itself. Yeah, so the answer is no. Yeah, it's just tough. It's just going to make it really tough for you to try and do that. So try something a little bit easier for yourself. Okay, good job. Let's take a look at example E. Set up an interval, find the volume of a solid rotation by rotating the function around y equals 4. What's the graph of y equals 4 going to look like? Which way? Horizontal. All right. So horizontal. Just going to draw on a horizontal line right there. Declare victory and go home. That's y equals 4. All right. Okay. So if we're going to rotate around this axis, try and write down for yourself what kind of a slice you're going to have to take. What kind of slice are you going to have to take for this one? Will, what kind of slice am I going to take? A dy slice or a dx slice? A dy slice, good. What kind of problems would I run into if I was trying to take a dx slice? Does anyone see? Yeah, you're going to be going from a curve to itself. So this one, there's kind of only one way to do it. Now, in some of these problems, there's two ways to do it. And if that's the case, and if I don't specify which way to do it, you're free to do it whatever way you see fit, whatever is most convenient for you. All right, so we got a dy slice. Find the volume of one shell. That's going to be volume is 2 pi r times the width, if you will, times the thickness. Now the thickness in this case is just dy. So there's two things you're going to have to figure out. One of them is the radius, and the other one is the width here. Now for the width, let me call that x and y. But for the radius, keep in mind we're rotating around this axis. So this distance, that's your r. Or there again is your r. Let's start by figuring out the radius. Now if this point is x and y, what are the coordinates of this point up here? Up on top. Close. Yes. X and 4. You thought you were wrong, but you're merely mistaken. All right, so 4 and y. Now this is where that stuff that I did earlier that, gets kind of annoying, is helpful. And that is where you do top minus bottom. That's how you're going to figure out the radius. So what's the top minus the bottom in this case? Well, you're going to be trying to find a distance vertically, so you're going to subtract the y coordinates. So it's going to be 4 minus y. But, yeah, actually, we can just leave it like that, 4 minus y. We don't have to mess with that at all at the moment. Now, how about the width? The width is going to be x minus 0. But x in our case is really what? Thank you. Cube root of the sine of y.
Cube root or is it times 3?
I believe it's cube root. Could be. Let's think here for a second. No, that'd be. I'm going. Yeah.
As long as we pick one.
Yeah. We'll make an executive decision. I'm guessing that it does look like 3 times the square root of y. I don't know. I've already written cube root. We'll go with the cube root. Yeah, but I have to admit, it does look like 3 times the square root of y. It's such a pain to get all these math fonts and things like that in your handouts. I apologize. All right. Let's put it all in here and find the volume of the one shell. So the volume of one shell is going to be 2 pi times 4 minus y times the width, which is going to be the cube root of sine of y dy. Nice. There's one last little problem that we're going to have to face here. If we're going with this as the cube root of y, then this is, it probably was a 3 there. 3 times the square root of y, that's okay. That's going to be, let's see, at pi, yeah, this would be a height of pi. Because at pi, this would be 0. 0 times 3 is going to be 0. That's going to give you your x coordinate there. So that point is at 0 and pi. Yeah, 0 and pi. Is that right? Yeah, 0 and pi. Yeah. 0 and pi. So our limits of integration then would be 0 to pi, because that's where we can stay within this region. I'm going to bring the 2 pi out in front. 2 pi times the integral from 0 to pi of 4 minus y times the cube root of sine of y dy. So that's the expression that we want. But as far as evaluating this is concerned, we're running into a small problem. What's that small problem? Anika? What problem might we be running into when we try and find this integral? Yeah, finding the antiderivative. In fact, there isn't one that I know of. So our alternative then is to do some numerical integration. So bust out your graphing calculators. Let's plug in this formula and try and find a numerical answer. Now in this case, I don't think it's going to work out to be anything nice and special, but we'll figure out in just a second. You're just being asked for something like this. Now sometimes if they work out nice, I'll ask you to give an answer as a fraction or involving a fraction. Let's find out what happens in this case. So we'll do math 9. The integral from 0 to pi. Now I know that we wrote our integral in terms of y's, but for purposes of putting it into your calculator, it's easier just to use x's. So wherever you see a y in your mind, just put an x. Now I'm going to put an extra set of parentheses in here. Parentheses 4 minus x, parenthesis, and then cube root. If you're looking for the cube root, you can go to the math button. Math, the fourth option down gives you the cube root. Did I click the right one? Something looks wrong there. Let me try that again. Math, fourth option down. There we go. Cube root of sine of x. Right parenthesis to close that off. Exit the integrand, and then put your dx term. And it's thinking. All right. Boy, that looks interesting. Is anyone curious about that number there? Yeah, it looks like 2 pi. So let's just divide by pi here. And I'm guessing that this does actually work out to be an exact answer of 2 pi. Keep in mind, though, that we have a 2 pi out in front that was left unaccounted for. So, yeah, it looks like 4 pi squared would be the exact answer. So you can do one of two things. You can either multiply by 2 pi at the end. So let's go back here. You change your answer and then multiply by 2 pi times by 2 pi. 2 pi. Yeah, and that does look a lot like 4 pi squared. Or you can just put the 2 pi in the integrand in the first place. I guess the reason I don't like putting it there in the first place is because it's nice to be able to look back and see if it's some multiple of pi. But the answer that they're looking for is a numerical approximation to the nearest fourth digit. So approximately speaking, 39.4874. Four pi squared? Not sure. How are we looking with that one?
So you said there's multiple ways to solve some of these problems. So would this one, for example, be like you gotta do shell or different method?
Yeah, I think that you run into problems with the washer method, right? We're seeing that same problem there that we saw in example D, and that is a DX slice is going to run into problems. Sometimes you can make it work, but if you're going from a curve to itself, I think that's screaming out to choose a different method.
So it'll be kind of like hints to kind of push you towards one method.
Yes, it absolutely would be. Yep, good question. Anything else? So I had to think, and this is probably something that I would give to you on the graph, but I had to think about what point this would be. Now, you're going to have an x-coordinate of 0 if this is 0. And this is going to be 0 when sine is 0. Now, sine is 0 down here when you put in a 0 for y, and sine is also 0 when you put in pi for y. So sine of pi is 0, square root of which is 0, times 3 is 0. So that's what brings you back to this point. That's probably a little bit more mental gymnastics than I would ask you to do on a test. My concern on a test is not so much that you remember your trig all that well here, but that you be able to set it up and finish it off. So I'd probably give you that point on an exam. Yes, James?
Is above where you put x4, is that the limits of integration? Where it says x4 in blue above the graph?
Y equals 4.
X in blue, Sharpie.
Oh, yeah, x and
Right
4.
above that, it says 0 y pi. Is that the limits of integration?
0.
Written on the
The
handout.
0 is
Oh, on the handout.
Yeah, 0 is x
The 0 is less
y,
than or equal to y,
which is less than or equal to pi. Is that the limits of integration?
0 to pi are the limits of integration, because to be inside of this region, you're going to have to be in the y range of 0 to pi. Anything beyond that is going to be outside the region. So
from the instructions, is this denoting that? Is that what that means when it says 0 less than or equal to y?
oh, this is just giving you the functions that bound your region. So let's take a look back at that for a second. That's a good question. And let me kind of do things this way. Let's see. So this function here is that much, right? And then let's see, what else do we have? X equals 0. Well, that's just the graph, that's just the y-axis, right? So it's telling you the functions that bound your region. And we want to stay within this region as we rotate around the line y equals 4, which is up here. So it's just telling you that, yeah, that's the region that we're going to rotate around this axis. Now, unless you want to hurt your brain too much or work harder than you want, I wouldn't necessarily try and imagine what this looks like. Just work with the stuff that you need, which is these things right here. All right, good on that? All right, thank you, appreciate the question. Okay, I think I'm gonna divide this up into a couple parts in terms of the video. So I'm gonna pause things here and we'll do a part 2.